Okay, so welcome to the third week of our statistics class. I am recording this today because two things. One is not everybody can make it to every class, and so I've decided from here on out to record it. And secondly, we go through quite a lot of stuff in the lecture, and it may not be so easy for you to remember it. So it would be probably not a bad idea to watch the video again for your revision, okay? Just to help cement the ideas into your head. So I've decided to record this from here on out. So they should be available online after the lecture. Give me a couple hours to encode it, then it'll be available online, okay? Okay, so we're back on our regular schedule. There's no snow, hooray. So the last couple of weeks, what have we talked about? So in the first week we talked about means, and we talked about standard deviations and standard errors. What's the difference between a standard deviation and a standard error? What do they tell you? Different things. Not you, somebody else. I know that you know. Anyone else? Yeah?
But standard deviation measures variability in data. Meanwhile, standard error measures how accurate your
estimate of the
value.
Right, absolutely. So there is a true mean out there somewhere, but we don't know what it is, right? Our sample mean is an estimate of the population mean, okay? But it's not going to be exactly the same, right? It's going to be a little bit different. So we take our sample mean, okay, and we say we think our population mean is around about 1.7, right? And our standard error tells us kind of the limits in which we think it most likely is, okay? So whereas our standard deviation tells us about the variability of the data, okay? Standard deviation, variability of the data, standard error, how accurately we can estimate the population mean, okay? So last week we talked about t-tests, and t-tests use the standard error in order to tell us whether or not two means are the same or whether they are significantly different, right? Is it likely that they share the same mean, or is it unlikely that they share the same mean, right? Are the means significantly different? So if you've got two data sets, okay, if you either got one for a one sample ANOVA, right, in which case you want to know, is this value different from a fixed number? That fixed number could be 0, or it could be 100, or it could be 972, or whatever. Or you've got a two sample t-test, okay, where you've got population A, population B, and you want to compare them and see, are they probably the same population, or are they different populations? Now there's two types of two sample t-tests. There's unpaired, right, which is what we use most of the time, and then there's paired, okay? Now I did a tutorial thing yesterday. Only one person turned up. I know I was very short on the letting you know about that, and I know some of you had classes, so I will make another tutorial maybe later this week, and then if you've got questions you can come along and ask, okay, and I'll try and explain things. But the one thing that we struggled with yesterday was the paired t-test. When and why would we use it? Okay, and we use it when we've got paired data, okay? So if you imagine we've got two samples from the same organism, right, then those two samples are always going to be pretty similar. If you measure or two samples from, let's say, closely related organisms, if you measure my height and then you measure my brother's height, they're probably fairly closely related, right? Because, you know, we share a lot of genetics, right? We share a lot of environment together. So in that case, it would be a paired sample, right? But if it's my height versus Nick's height, then it wouldn't be paired, right? Because we don't share any genetics together, as far as I'm aware, okay? I don't think my father ever went to America, so maybe it's okay. And we don't share a common environment, right? He grew up in America and I grew up in Scotland, so there's no reason to pair us, right? So if you wanted to look at unpaired things, then use the regular t-test. If it's two things that are closely related for some reason, use a paired t-test. And a paired t-test is stronger because it takes account of background variability in a way that the unpaired test doesn't. So that's if you've got two samples, either one or two samples. What if you want to compare means between three or more? In that case, you use this test, analysis of variance. So our ANOVA, come on. Okay, my computer's decided to completely hang. Good job, Sony. Good thing they don't make computers anymore, isn't it? We're sorry, something went wrong. I know. Let's try starting this again. Okay, well, that's thinking about things. I'll start talking about something we've talked about already. Okay. Okay, this idea, our data points. Okay, equal a model plus variation. Okay? Okay. Yeah? Okay. So let's imagine we've got two models. Okay? Okay, we're going to call the first model bad. Bad. Okay, we call the second one good. Okay, so we've got two models. One is a bad model, it doesn't fit the data well. And the second one is a good model, and it does fit the data well. Yeah? Okay, so we can't compare the models directly, but we can compare these. We can compare the error terms, right? If our model is a bad model, there's going to be lots and lots and lots of error left, right? It's not going to fit close to the data points, so there's going to be a lot of error. But if you've got a good model, then this error term will be much smaller, right? This is the fundamental idea behind ANOVA, right? It's how well does this model fit to the data, right? If it fits badly to the data, the error term will be very large. If it fits well to the data, then this error term will be small. Okay? So in this case, that would be small, right, because the model's good, and this would be large because the model's bad. Okay? This is the fundamental idea behind ANOVA. Okay? You're going to fit two models and you're going to compare them against each other. Okay, let's try again. Hooray! Okay. So ANOVA, this test, it's really, really widely used in biology and in science in general. We use it for looking for differences in 3 or more treatments. And why do we use this so much? Well, a big part of it is that it's extremely versatile. It can be used to do lots of different things. Okay? You can use it with very large data sets, with very, very, very many comparisons. You can identify interacting variables, right? So maybe we're doing an experiment where we are looking at plant growth and we're looking at the effects of light and nutrient status, right? Each of those is going to have an effect. Light is going to have an effect and nutrient status is going to have an effect. But they might interact with each other, right? It might be that if you grow them at high light and high nutrients, then they grow much, much, much bigger than what you would expect by looking at each one individually. That's what an interaction is fundamentally. And then we can also use things called post-hoc tests to identify specific differences. So this will make more sense when we kind of go through a little bit. So, as I said, fundamentally we're comparing two models. Model bad and model good. Okay? Okay. Now the first model is the null hypothesis. Okay? And for the null hypothesis, what we're going to do is we're going to use the grand mean. Okay? This is the mean of all of the data points. Okay? This is the average for all of the data points. And our second model are individual means for individual treatments. Okay? Now, this sounds a little bit weird, but give me like 30 seconds and you'll see an example and it'll make a whole bunch more sense. Now, if you've got individual means for individual treatments, it will fit the data better. But the question is, how much better? Is it just a little bit better, or is it a lot better? Now, I'm going to show you two examples. Okay? One is where the ANOVA would not be significant. Right? That's the first example. And then the second example is going to be where the ANOVA is significant. Okay? So here's our first example. So here we've measured photosynthesis, okay, photosynthetic rate, and you've got units up here, and we've got three groups of plants, okay, group A, B, and C, okay, and we measure their photosynthesis, and these data points are the values that we get, okay? Everyone with me so far? Okay. So this red line is the grand mean. What I've done is I've taken the average for all of the data points, right? I just add this value to this one, to this one, to this one, to this one, right, all the way through, add them all up, and divide by the number of samples, right? So I take the mean for all of the data, okay? This is my null hypothesis, okay? So this is my null hypothesis, that this mean describes all of the data, okay? Now remember, data points model plus error, so we need to quantify the error. And the way that we're going to do this is we're going to calculate the sum of squares. Sounds harder than it is, okay? So all we're going to do is we're going to take away each data point away from the mean, right? So we take this data point away from the mean, we take this away from the mean, we take this away from the mean, we measure this distance, this distance, this distance, right? We measure all these distances, yeah? And some are positive and some are negative. And if you add them up, you'll get 0, right? Must be true, right? Because it's the average. So what we're going to do is we're going to square them. Remember we did that when we measured standard deviation. We took these differences and then we squared them and then we added them all up. Okay? And we get what's called the sum of squares. Right? So we did this for standard deviation. Yeah? We measured this thing called sum of squares. Now our sum of squares here is 2,337. Okay? This is our null model. Right? This is our null model. Treatment has no effect. Okay? So your treatment A, treatment B, treatment C. The null hypothesis is that the treatments have no effect. Right? And if the treatment has no effect, then the mean of this group and the mean of this group and the mean of this group will be the same. Yeah? With me so far? Okay, good-o. So here's our alternate hypothesis. Our alternate hypothesis is that the mean for this group and the mean for this group and the mean for this group are not the same. Right? So this is our second. This is our good model. Okay? So we take the mean for this group, for all these blue points, and here it is. We take the mean for this group. Okay? That's all those points, and we take the mean for this group, and that's all these points, yeah? Okay, with me so far? Okay, and we're going to calculate the sum of squareds for these, right? So here's, you calculate the sum of squared for this one, and then this one, and then this one, yeah? Okay. And we can get sum of squared values for those, so it's 424 for here, and 776, and 937, yeah? Okay. And if we add those all up together, it's going to give us a value of 2,137. Okay? So our null model gave us 2,337. Our individual means model gives us 2,137. So there's not so much difference between those two. Everyone okay? Do you want me to go through that again? No? Super quickly. Okay, super quickly. Null model. Okay? Null hypothesis. Treatment has no effect. Treatment does nothing. If treatment does nothing, the mean for this group and the mean for this group and the mean for this group will be the same. Okay? And if all the means are the same, that means that the grand mean would be basically the same, right? Yeah? Okay, grand mean, take the difference between the mean and the data points, square it and add it together. Gives you 2337. Okay? Alternate hypothesis, the means are different. Okay? Here's the first mean, here's the second mean, here's the third mean. Okay? Calculate the sum of squared for each of these. Right? Sum of squared for this, sum of squared for this, sum of squared for this. That gives you those values. Where's my clicker? Put it down here. Okay? That gives you these values up here, and if you add those together, it's going to give you 2137. So, if we look at our total variation was 2,337, right? That was for our grand mean, yeah? So, our total variation 2337, but most of it is unexplained by the new model, right? So here's our old model, our null model, okay? 2337.4, right? We calculated that one. Here's our new model, 2137.3, okay? Now the difference between these two is about 200, okay? The difference between those two is just about 200. Did you get handouts? Yeah? Okay, good. So the difference in these two is about 200. So if we look at that 200 and we say 200 divided by the null model, right? That's about 9%. So our new model, it doesn't fit the data very much better. A little bit better, right? But of course it's going to fit the data a little bit better, right? Because of course, these means are going to be better, right? The more factors you put in, the better it's going to fit the data. But it doesn't fit the data very much better. It's only about 9%. Okay? So in this case, that ANOVA would not be significant, right? Now I haven't done the math to show you that, because it's not all that exciting and interesting, okay? But I'm going to show you one where it does work next, and we'll go through all the math on that one, okay? So, here's our second scenario, okay? We've got our three groups of plants, okay? We've grown these plants under low nitrogen, medium nitrogen, high nitrogen, okay? Okay, so we've got low, medium and high nitrogen plants. Our null hypothesis is there's no difference between these three groups. Okay? Model 1. Null hypothesis, no difference between the three groups. Which would mean that the average for this, the mean for this group, and the mean for this group, and the mean for this group are all the same. Yeah? Okay. Okay. So, if we calculate our sum of squareds, you take this distance, this distance, this distance, you square them, you add them all up, right? And it's going to give you a value of 2368. Okay? 3268. 3268, okay? That's my total variation. Now I'm going to use my second model, okay? Where we're going to calculate individual means. So we calculate a mean for this group, calculate a mean for this group, and you calculate a mean for this group. And we're going to do the same thing. We're going to calculate out the sum of squareds, right? Now the sum of squareds this time gives me 2047. Okay? 2047 for this model. Okay? So you've calculated this and you've calculated this. Yeah? Happy. So the total variation, 3268. About 2/3 of that variation is not explained by the new model, but about 1/3 is. Okay? And I'll go through the math here. 2368, this is our null model. Okay? Minus 2047. Right, this is our new model. Okay? So this much is explained by the new model, this 1220. Okay, or 1221. This is explained by the new model. Right? And this is not explained by the new model. Right? Okay. So take that 1221, divide by 3268, and that gives you 37%. So the new model explains about 37% of the variation. It doesn't explain 62.6%. Okay? So you see this number, it's much higher than 9. Yeah? Much better than 9. But this is not a statistical significance, and we want to calculate out the statistical significance. Now, this is actually fairly simple. We're going to use what's called an ANOVA table. Okay? And an ANOVA table looks like this. Okay? And up here it's got source of variation, between groups, within groups, and total. Well, we know what our total is, right? 3268. Yeah? And we know that the total variation within the groups is 2047. Okay? This plus this plus this is 2047. Right? That's the variation within the groups. Yeah? Okay. Our total variation this way, right? Okay. So that's our total variation. That's the variation within the groups. And this 1221, this is the variation between the groups. Okay? It's called between groups variation or among groups variation. Okay? But basically, if you add these two together, you get this one. Okay? This is the new model. This is the null model. And this is what's explained by the new model. Yeah? This is explained by that model. Our degrees of freedom. Okay. 2 and 27, you're saying, how do you get to this? Okay. Well, between groups, how many groups do we have? 3 groups, right? 3 minus 1 is? 9, yes. 3 minus 1 is 2. It's a joke. Really, really bad joke, okay? I just saw the confused expression there, like, huh? Yeah. 3 groups, minus 1 gives you 2, right? So 2 degrees of freedom, right? Because there's 3 groups. Okay, within groups, and it says 27 here. Okay, now the reason it says 27 is you've got 3 groups of 10. Okay, 10 minus 1, 2. Okay, 9, okay? 9 times 3, 27, okay? So that's where that 27 comes from. You take away 1 from each group, and then you add up all the groups, okay? Total, 29. 2 plus 27? 92. No, 29, okay. Okay. So, MS, mean square, okay? How much of this variation is there per degree of freedom? Right? Degree of freedom, it corrects for size. Right? It corrects for size. So there's 3 groups. So there's 2 degrees of freedom. So you've got this much. This 1221, this is explained by 2 degrees of freedom. Right? So how much is there per 1 degree of freedom? So you take 1221, you divide by 2, and you get 610. Okay? So there's 610 units per degree of freedom. 610 units of variation is explained per degree of freedom. Okay? Over here, this is the within groups variation. This is how much variation is left by the new model. Okay? Now there's 27 groups, right? Because there's 9 degrees of freedom for each group, right? Because there's lots of data points in here. So you're going to take this, you're going to divide by 27, and it's going to give you 76. Okay? So this is how much variability there is per data point. This is how much variation there is for each data point. Okay? And then if you divide this 610 by 75, you get this value called F. Okay? Now F is just, it's the ratio of variability explained by the new model divided by unexplained. Right? So F is basically, I need a lighter colour, okay? So explained variation unexplained. Okay? And that's what f is. Okay? So this much variation was explained by the new model. And this much wasn't explained by the new model. This bit was left over. This is unexplained variability. And this is explained variability. Yeah? So that gives you f, yeah?
What do you mean by explained variability?
Oh, okay. So this variability in the data is not explained by this line. Right? It can't be, okay? Because this line just gives you the average for all of these data points. Yeah? So this is variability which is just coming from the randomness of the data. Right? It doesn't correspond to the mean particularly. Right? So that's just unexplained variation. Right? Just random noise in the data. If our null hypothesis is true and there's no difference between these three groups, then this is the variation that you would expect, right? So this is the total variation. This is the variation, the unexplained variation within these groups. And the difference between these two is explained by the model, right? If we use the null model, this is our variation. If we use the new model, our variation goes down. So some of that variability from the null model has been explained by the new model. Do you understand what I mean? It's reduced that variability down. It said that if we use these means, we're going to get less variability. So these means explain some of the variation. They take it away. Right? Everyone okay? Right? So this is explained by the new model compared to the old model. Okay? And this is not explained by the new model. Right? So when we say explained variation, it means it's explained by the new model compared to the null model. Right? So it's the difference between the null model and the new model. Okay. Okay. So you have to correct for the number of degrees of freedom in order to get rid of effect sizes. We have 30 data points, okay? And it generates this much variation. If we had 300 data points, this number would be 10 times bigger. Right? Even if we still had only 3 groups. So you need to correct for the size. Okay? Otherwise it doesn't make any sense. So this divided by the degrees of freedom, it corrects for the number of samples. Okay? This top one corrects for the number of groups. I know this is hard. I get it. Except for you. It's easy for you. Hard for everyone else. Okay. So this corrects for the size, and it gives you this f. So how much of the variability is explained by the new model compared to how much is unexplained by the new model? And it gives you this f of 8. Okay. Now, we're not going to worry about the f distribution, right? It's just another data distribution, or probability distribution, and we're not going to worry about what it looks like, okay? If you're really interested and excited about what it looks like, I can draw a diagram, a very rough diagram, but the f distribution looks kind of like this, where this is a probability. But we're not going to worry about that, and then this is going to be degrees of freedom. Is it f? Okay. We're not going to worry about that. Okay. We're just going to stick this into Excel. Okay? Excel can calculate the p-value for you. Okay? So instead of using t.dist, which is what we used for the t-test, we use f.dist. See, Microsoft people, they actually are pretty logical on at least one thing. Okay? f.dist.rt, so we put in f in here, degrees of freedom 1, degrees of freedom 2, and it'll give us our p-value. Okay? So f.dist.rt, and then 8.05 from up there, degrees of freedom 1, 2, degrees of freedom 2, 27. And it's going to give us a p-value of 0.00181. So, are we going to accept the null hypothesis that all of the groups are the same, or are we going to reject the null hypothesis that the groups are significantly different from each other? We're going to. Who thinks accept? Who thinks reject? Who doesn't know? Who doesn't care? So remember that we've got an fairly arbitrary p-value cut off, right, which is 0.05. If it's less than 0.05, we reject the null hypothesis. Okay? Now remember, our null hypothesis is that there's one mean for everything. Okay? That the grand mean is a good explanation of our data. Right? This is way, way, way smaller than 0.05. And so we're going to reject the null hypothesis, and that we're going to accept the alternate hypothesis. And our alternate hypothesis is that individual means are better. Right? That the individual means are better, that they explain the data better. So by rejecting the null hypothesis, we're going to say that there is a significant difference, a real difference, between at least two of the groups. Right? At least one group is different from the others. But we don't know which one. Okay? So let's just look at the data again and think about that. Okay, this is our null hypothesis. Null hypothesis is, this is a good description of the data. Okay? Who thinks that this is a good description of the data? Nobody. Okay. Alternate hypothesis. This is a good description of the data. Who thinks that this is a good description of the data? Or at least a better description? Yeah, most of you, right? It makes sense. Yeah? But what it's telling us is that this is significantly better. Statistically significantly better than the null model, right? We're going to reject that. We're going to say that that is probably not true. Okay? And if that's probably not true, this probably is true. Okay? At least one of these groups is different from the others. Okay. Now, there's a little problem with ANOVA. Because ANOVA, it just gives you one p-value, right? It doesn't tell you which group is different from the others. It can't do that, right? It can't tell the difference. So if you want to do that, then you need to use something called post hoc tests. Okay? Now, this sounds fancy and hard, but it's actually pretty easy. Okay? It's literally like you press one button and you press one checkbox in SPSS and it will do magic for you. Okay? But you have to know which buttons to press, otherwise you might get nonsense. Okay? So ANOVA tells us that there's a difference between at least one of the groups. It says that at least one of the groups is different from the others. It could be that all three groups are different from each other. But it could be that two groups are the same and one is different. Okay? So we're going to use a post hoc test, and the test that we're going to use is called the Tukey's test, okay? Or the Tukey's-Kramer test, the Tukey-Kramer test, or Tukey's HSD. HSD stands for Honestly Significant Difference, okay? Which I think he might have been building it up a little bit there, but it's actually a pretty good test, so I'll let him away with it. Okay, now Excel can do ANOVA, but it can't do post hoc tests, right? because Excel, it kind of sucks in some ways. It's pretty limited, right? So this is why we can't use Excel. We can use Excel up to a point. We can use Excel for things like t-tests. But if we want to get to hardcore statistics, which we do because it's fun, then we're going to need to use SPSS, right? Which is why I'm teaching you SPSS. Yeah? So it makes sense now, doesn't it? Yeah? Okay. So SPSS can do post-hoc testing. We're going to use Tukey's test. So literally, as I say, it's one button in SPSS, and I'm going to show you how to do this on Thursday, okay? But when you do the Tukey's test, okay, it says Tukey's HSD here, okay? It says multiple comparisons and variable PS photosynthesis, Tukey's HSD, and then it's got a table, and it says group. It says I and J, group and group, okay? So it's got group 1 versus group 2, group 1 versus group 3, group 2 versus group 1, group 2 versus group 3, 3 versus 1, 3 versus 2, yeah? And it will tell me what's the difference in the means between these two groups, okay? So here it says the difference between group 1 and group 2, the mean difference is 4.9, okay? And the mean difference between group 1 and group 3 is 15.3, okay? Now, actually, I'll show you that in a second, okay? And it says 2 versus 1 is 4.9. Well, we know that has to be the same as that one. 2 versus 3 is 10.4, okay? Okay. It tells me the standard errors, 3.89, okay? Well, you know how to calculate our standard errors. We can do this, okay? And then it tells me the significance. Now this is the p-value, okay? So it says group 1 versus group 2, significance 0.43. Now our null hypothesis is that there's no difference between groups 1 or 2. Okay? Null hypothesis, no difference between groups 1 and 2. Do we want to accept this null hypothesis, or do we want to reject the null hypothesis? Who thinks we will accept the null hypothesis? Who thinks we will reject the null hypothesis? Okay, we're going to accept the null hypothesis because this is bigger than 0.05. We only reject the null hypothesis when this is smaller than 0.05. Okay? So we're going to say that group 1 and 2 are not significantly different from each other. Okay? Okay, yeah?
0.02, then why do we accept it?
Because you're looking at the wrong line.
Oh.
Significance 0.43, top line. Right? 0.43, okay? We will accept the null hypothesis. Okay? Groups 1 versus group 3, mean difference 15.3, standard error 3.9, significance 0.002. Null hypothesis, group 1 and group 3 are the same, or are not different, okay? Are we going to accept the null hypothesis or reject it? Who thinks we will accept? Who thinks we will reject? Oh, I'm so bringing chocolate for you guys next week. I'm not. No, but I would. You can think that I would. I've been told it's the thought that counts. Okay, I'm thinking about it. Group 1 versus 3, okay? Significance of 0.002, right? So this is significantly less than 0.05, and so we reject the null hypothesis. So groups 1 and 3 are not the same, okay? Okay, let's look at group 2. Group 1 and group 2, well, we know they're the same, right? Our P is 0.43, okay? So they're the same because these were the same, okay? Group 2 versus group 3, p-value of 0.033. Null hypothesis, group 2 and group 3 do not differ significantly. Are we going to accept the null hypothesis or reject the null hypothesis? Right. So we reject the null hypothesis. So if our null hypothesis is there's no significant difference, we reject the null hypothesis, so we say there is a significant difference. Okay? And then if you look at group 3 versus 1, group 3 versus 2, both of those are significant. Okay? So if we look at our data again, what we're saying is that these two groups are not different from each other, right? But this group is. This group is different from this group. This group is different from this group. Okay? That's what this is telling us. There's no difference between this group and this group. Okay? Now you might look at them and say, well, yeah, but look, those data points are higher and these data points are lower. Sure, but probably this data point is increasing the variability. So we can't be sure that there's a significant difference between these groups. With only 10 replicates, we can't be sure. But if we'd measured 100 plants, if there is a difference, we would find it. So a lot of it comes down to replication. More replication means that you're able to find those differences more easily. Mathematically, why is that? If we had 100 replicates here, and 100 here, and 100 here, okay? Right now we've got 10, 10, 10, 10, right? But if we had 100, 100, 100, let's go back to our ANOVA table. Our within groups variation, now it's 9 degrees of freedom for each group, right? 9 plus 9 plus 9 is 27, okay? If we had 100 replicates, then the degrees of freedom would be 99. So it would be 99 plus 99 plus 99, okay? 297, okay? And then this number would be really small, okay? And f would become really big, yeah? Because you'd be dividing this by a very, very, very small number. So this would become big. So if you've got more data, if you've got more replication, you will increase this number here, right? And you'll make this small, and you'll make this big, and it'll be easy to find differences. So more replication is going to make that f value bigger. Does that make sense? Yeah? And remember, when we calculate standard error equals standard deviation divided by square root of the number of samples, right? Okay. So, if we've got 10 samples here, square root of 10, it's like 3, right? If we've got 100 samples, square root of 100 is 10, okay? So the standard error gets smaller with the bigger sample sizes. So your Tukey's test would become more powerful too. So the more replication that you have, the easier it is to find differences. Okay? Okay. Good-o. So this is what we're saying, okay? These two groups, they're not significantly different, or we can't find any significant difference given 10 replicates. Okay? If we had 100 replicates, maybe we'd see it. Maybe we wouldn't, right? Maybe there really is no difference. But this group, we believe to be significantly different from these two. Okay. Everyone happy? Watch the video again, read through your notes again, it'll make more sense. Okay? Or maybe not. So, some assumptions. Our samples are randomly sampled. Okay? We're not just choosing the biggest plants, right? We're choosing plants which represent the sample. Okay? Or represent the population. Our sample measurements were independent, okay? What do I mean by independent measurements? So if I measure, let's imagine that I have a scale for measuring weight, right? And I step on it, and it says 1 at a time, please. Okay? I step on the scale, and it measures my weight, and it says 180 kilograms. Okay, and I get off, and Daniel gets on, and it's going to measure his weight independently, right? It's going to say 73 kilograms. I don't know how heavy you are, but you're 73 kilograms today. Okay, so it doesn't matter what I weighed. His sample measurement is independent, right? But let's imagine that I got on, and it said 180 kilograms. And then he got on and it said, well, the last guy was pretty heavy, so I'm going to make you 150. let's imagine it remembered the sample before. Then the samples wouldn't be independent, right? So this is really important. So I talked about independent samples before, and I didn't explain it, right? So I want to just make sure that's clear, so that when you measure each individual, there's no memory of the one before, right? Each sample measurement is independent. There's no bleeding across between measurements. If you get that, it will underestimate the variation in the data, okay? So they have to be independent, okay? So if you measure me, and then you measure him, and then you measure Nick, and then you measure Gunther, it doesn't, like what it measures from me is not going to affect his measurement, right? And what's measured by him is not going to affect his measurement, right? That they're all independent from each other, okay? And this can be a problem for related samples, okay? If you measure identical twins, right? Okay, or even fraternal twins, they're going to be more similar to each other. They wouldn't be independent samples, okay? We need to use paired tests in that case. Population should be roughly normally distributed. It doesn't matter too much actually for ANOVA, because ANOVA is what we call a robust test. It doesn't really care that much about this one, okay? It's pretty strong. And our standard deviation values have to be approximately equal. This is called an assumption of heteroscedasticity. Try saying that when you're drunk. Anyway, there are tests for that. One test in particular called the Levene's test. We're not going to worry about it, okay? The data I'm going to give you is going to be approximately equal in standard deviations. Okay, so was that nice and easy for everybody? Everyone is suitably like, come on, Lewis, you're wasting my time here. Who wants to make it harder? Me! Okay, I'm going to make it harder for you. But don't worry, this is a very logical progression. Okay, let's imagine we want to do a more complex experiment, okay? And we're going to do an experiment called a 2x2 factorial experiment. It's going to be my example, okay? We're going to do a complex experiment with multiple treatments. And in this case, you're going to use multiple ANOVA, okay, or MANOVA. Okay, so this is more complex. So I'm going to give you an example. So let's imagine that we're interested in the effects of diet and stress on weight gain in mice. Okay? So we've got a bunch of mice and we want to know, does their diet affect weight gain and does their level of stress affect weight gain? Okay? Who's put weight on since they came to college? Or who put weight on immediately upon coming to college and has subsequently lost it through starvation? I know this. So there's a thing in America they call the freshman 10, right? 15, okay. So after you leave home and you come to college, you put on like 15 pounds in the first semester, right? And the idea about this is kind of, I suppose, two main things, I suppose. One is you eat a whole bunch of junk food, which you probably didn't eat at home, right? And then the other thing is you're probably a lot more stressed, right? And stress will make you gain weight. So let's imagine that we're interested in studying this. So we get a big bunch of mice. We get 32 lab mice and we split them into 4 groups. Okay? Control, low stress, control, high stress, junk food, low stress, junk food, high stress. Okay? This is going to be our test. So we've got 2 factors here. Okay? Control versus junk food, low stress versus high stress. Okay? And this has all the factors, okay, combined. So this is called a factorial experiment. So we can think about this: control, junk food, low stress, high stress. Okay, control food, junk food, low stress, high stress, yeah? 2 by 2, yeah? Easy peasy. Okay. So the 2 by 2 factorial experiment with 8 replicates. How do I know we've got 8 replicates? We have 32 mice, we have 4 treatments. Okay, 32 divided by 4 is 8, yeah. Okay. So, here we have our data table. Okay, we've got 4 columns of data. Control low stress, control high stress, junk food low stress, junk food high stress, yeah? All different possible ones. And we're going to measure weight gain in milligrams per week, okay? So 124, 131, 122, 129 milligrams per week, right? And you can see we've got this filled in for all of them, okay? Now at the bottom we've got means, okay? 124.75, 132, 132.5, 152.25. And we've got our ranges in here, right? Remember, our range is just our biggest and our smallest data points. And you can see the ranges overlap, 119 to 134, 124 to 143, 120 to 142, 140 to 162. So you can see the data overlaps with each other, okay? So how are we going to analyze this? Well, we're going to use, I should mention, stress is induced by rap music, okay? Yeah. Control is Beethoven. Nice, relaxing Beethoven versus... they're probably just worried they're going to get a cap popped in their ass or something. I don't know. Whatever it is you young people do nowadays. And then our control mice, they get mouse food, okay? And then our junk food ones get fed potato chips and Coca-Cola. And no, you can't volunteer to join this trial, okay? So these are getting mouse food, these are getting junk food. They're getting nice relaxing music, okay? They're getting kind of stressed out music. So this is our test, okay? Okay. Now, we're not going to go through all the math in this one, okay? But we will bring up the ANOVA table, okay? Now, it looks a little bit more complex, but it's actually not that much more complex, okay? So, we calculate out the sums of squares, okay? For all of these different groups, okay? And you'll see here it says diet, stress, and then diet by stress. And this is our interaction, okay? So, these are our sums of squares. Now, let's think about our degrees of freedom, okay? How many diet levels did we have? 2, right? 2 minus 1 is? 1, yes, okay. Stress, how many stress levels did we have? 2, right? 2 minus 1 is? 1, okay. We're going to take 1 degree of freedom for the interaction. We've got 1 interaction here, right? So we're just going to take 1 degree of freedom for that. And then our error is going to be 28, okay? Now, I want to explain how we get this one. We have 32 mice, okay? Minus 1. So 31 mice, okay? 2 diet levels, minus 1, okay? So we're now at 30 degrees. 2 stress levels, minus 1. So we're now at 29, okay? And then 1 stress by diet interaction, and that's going to be 1 more. So 32 minus 1, minus 1, minus 1, minus 1, gives us 28. So 28 degrees of freedom here. Now, it doesn't matter if you can remember how to calculate these things, right? It doesn't matter, because SPSS will do it for you, okay? But I just want you to understand the principle first, so that when you look at the SPSS output, it doesn't just seem like complete nonsense, right? I want you to understand what the numbers mean. So here's your degrees of freedom here, okay? And so your sums of squares and your degrees of freedom. So 1568 divided by 1 is 1568. Boom. Okay, even I can do that math. Okay, so we go down through here. 1353 divided by 28 is 48.32. So what we're going to do is we're going to divide this by this, this by this, and this by this. Okay? And it's going to give us these F ratios. So it's this ms, mean squared, divided by the mean squared for the error term, okay? So 1568 divided by 488 gives you 32, okay? 1458 divided by 48 gives you 30, okay? And if we look this up using our f-test again, you're going to get these p-values, and it says p is less than 0.001, p is less than 0.001, and p is 0.017. Okay, so null hypothesis. Diet has no effect. Do you accept or reject the null hypothesis? Reject, right? P-value is less than 0.05. Null hypothesis, diet has no effect, right? We reject that. Diet has not no effect, right? Means diet has an effect. Stress, null hypothesis. Stress has no effect. Okay, accept or reject? Reject, right? So stress has not no effect. Okay, stress has an effect. Diet by stress. Okay, there's no interaction between these terms is the null hypothesis. Null hypothesis, there's no interaction between these two factors. Do we accept or reject the null hypothesis? Reject the null hypothesis, right? So what we're saying is that there is an interaction. Okay? So, diet is significant, stress is significant, diet by stress is significant, okay? It says there's an interaction. It says, what does this mean? Okay? Let's try to understand this with some graphs. Okay, so I've got 4 graphs here that I want to go through. Okay, so okay. Control, junk food. Okay? Control, junk food. Okay? Red line, stress. Blue line, control. Okay? Okay. Example 1. Diet has an effect, but stress has no effect. Okay? So this is mass up here. Okay? Diet has an effect. These are bigger than these, right? Junk food, control food. Yeah? But stress has no effect, right? Because the two lines are on top of each other, right? So if diet has an effect, the mice which are fed junk food will be bigger than the mice which are fed control food. Yeah? Happy? Okay. Example 2. Diet has no effect, but stress has an effect. Okay? Control mice, mice fed junk food. No difference. Right? Equally big. But the stressed mice are heavier than the control mice. Make sense? Okay. So that's if you've got no this is where diet has an effect but stress has no effect. This is where diet has no effect, stress has an effect. Okay. Example 3. Diet and stress both have effects, but there's no interaction. Okay? So the mice which are fed control mouse food are lighter than the mice which are fed junk food. Right? If you give them junk food, they get heavier. Yeah? Okay. But also stress has an effect. The stressed mice are heavier than the control mice. So these lines are parallel. And this is essentially 1 plus 2. This added to this. Right? If there's no interaction, you can add these together to get this. Okay? Okay. Final one. Diet and stress have an effect and there's an interaction. Okay? So the mice fed control food, mice fed junk food. Yeah? Okay. The ones which are fed junk food are heavier. We see that stress has an effect, right? Because the stressed mice are heavier than the unstressed mice. Okay? But the lines aren't parallel anymore. Right? They diverge from each other. And this is a multiplicative effect. This is this multiplied by that. So this is a multiplicative situation. You get this. Why is this interesting for us? Okay. Let's imagine that we did 2 experiments. We did one experiment which just looks at diet, okay? But not stress, it just looks at diet, okay? We'd get this line, okay? Let's imagine that we did one which looks at stress, but not diet. We could get this, right? This difference anyway. We wouldn't have this line, right? But you get a difference, right? Okay. But you couldn't get to this. If you look at the 2 factors independently, you can't find this relationship. This is why you do a ANOVA. This is why you do a complex experiment. It lets you work out if factors are interacting with each other. So what it's saying is that if you're stressed and you eat junk food, you will gain weight more rapidly than if you are unstressed and you eat junk food, or if you eat junk food and you're not stressed, or both of those combined. Right? It's saying that you get a factor which is bigger, right? The 2 of them are kind of doing something together. Okay? Now, we're going to do this in practical on Thursday, okay? So it will hopefully make more sense. Let's run through it again just really quickly. Okay, so we've got our ANOVA table here. We understand about diet. We understand about stress. The one that we are trying to understand now is this interaction, yeah? So we reject the null hypothesis, we reject the null hypothesis, we reject the null hypothesis in all 3 of these. Okay. So diet is significant, okay? If you feed them junk food, they get fatter, okay? If stress is important, if you stress them, they get fatter, okay? And then there's an interaction between those 2 things. So just running through these again. Example 1, diet has an effect, but stress has no effect, okay? The ones you feed junk food are bigger, the ones that don't get junk food are not. These 2 lines are right on top of each other, okay? I appreciate in this example, on this graph, they're not exactly on top of each other. That's just the way that PowerPoint works, okay? If I did put them on top of each other, you wouldn't see one of the 2 lines, okay? So I put them just really close to each other, okay? It's just meant to represent that they're no different, okay? So diet has an effect, stress has no effect, okay? Diet has no effect, but stress has an effect. Feeding them junk food, feeding them controlled food, no difference. But stress has an effect. If you stress them, they put on weight, and if you don't stress them, they don't put on so much weight. Yeah? Okay, so each of those independently. Now you can either add them together, or you can multiply them by each other. Right? So if you add them together, diet and stress have an effect, but there's no interaction. Okay? Feeding them junk food will make them bigger. Stressing them will make them bigger. But there's no interaction between those 2 terms. Right? There's no multiplication. It's just additive. Okay? You could do this experiment, you could do this experiment, you could add them together, and you could get this. Okay? But example number 4, diet and stress have effect, and there's an interaction. Okay? Give them junk food, they get bigger. Stress them, they get bigger. Give them junk food and stress, and they will get even bigger than what you would predict for each thing independently. So it's saying that there's some multiplicative effect, right? The result is even bigger than what you would expect by studying each thing individually. So when we say there's an interaction between the factors in a 2-way ANOVA, we're saying that the increase or the decrease is larger than we would expect by studying either factor by itself. Right? It's showing there's something more complicated going on. Right? If you eat junk food and you're stressed, you will put on weight faster than if you were just eating junk food or you were just stressed. Okay? Now Excel, unsurprisingly, can't manage a two-way ANOVA, but SPSS, also unsurprisingly, can. Okay. Everyone happy? 10 minutes left. We're nearly there. Nearly there. Okay. The last little bit is just mainly for kind of interest, right? Okay. Or boredom, whichever you prefer. So MANOVA. So you can do even more complex models, right? In our brain, you know, we could do an interaction model here, right? We could have two factors, right? We can plot this out on a graph. We can plot out a graph, right? If we've just got like one factor, A versus B, okay? A, B, and then ink mass, okay? Okay, so, okay, easy, right? One factor. Okay, what if there's two factors? Now we have 3D graph, okay? A, B, X, Y, okay? So you can think about this as going kind of that way, right? So you've got these two in front and these two behind, okay? That's if you've got two factors, okay? So this could be light level. This could be temperature. Okay, and then this could be photosynthesis. Okay, so light along this axis, temperature along that axis, photosynthesis up this axis, right? So that'd be two factors. What if I want to do three factors? Now unfortunately my blackboard doesn't let me do that, because my blackboard is a two-dimensional thing. I can draw three-dimensional things on two-dimensional things, but I can't draw four-dimensional things. Unfortunately, I don't know what a four-dimensional thing looks like. What if I wanted to add another factor? And I could have a five-dimensional graph. I don't know how to plot that one out. What about a six-dimensional graph? What about a 10-dimensional graph? Now mathematically, we can do that, right? SPSS doesn't care, okay? SPSS and Honey Badger. What a pair. Okay, they don't care how many dimensions you want to add, but we can't graph it, right? Our brain doesn't work in multiple dimensions, okay? Limited beings that we are. So, if we want to do that, then we need to use MANOVA. Now, you can do as many dimensions as you like, but the problem is it becomes harder and harder and harder to work out what's happening the more dimensions that you add, okay? Once you get beyond about 3 or 4 different treatments, it just becomes soup. You're not able to really say what happened, right? It just becomes too complex for your brain to figure it all out. But I'll give you an example, okay? Recent paper I just submitted, okay? Looks at the effects of, it's a germination paper. We're looking at germination percentages. We looked at 2 different species. We looked at a mixed versus a single treatment, so either the seeds were separate by themselves or they were mixed together, okay? We had 3 different nitrogen levels and we had 3 different salt levels, okay? So 1, 2, 3, 4-way ANOVA, okay? Or MANOVA, okay? Another thing that we call this is GLM. We'll call it GLM from now on because it'll be easier for you to think about. So it is possible to analyze something like this. I did it. It wasn't easy, but I did it, okay? But once you get anything like this way, or even this is probably too complex, actually. What I actually did was I actually split the data. So I analysed each species separately, because then that way the analysis made sense. You can do more complex analyses, don't do them, right? You will never understand the data. So let's have some conclusions. Okay, if we want to test for a difference between 2 means, A versus B, we use t-test, yeah? Okay, t-test A versus B, super easy to interpret, right? A and B are either different or not different. Okay? Easy peasy. If we want 3 or more means, we don't use ANOVA. We don't use t-tests, we use ANOVA. Okay? And we're going to use a post-hoc test. Now you're going to say to me, hey, but Lewis, why don't we just use more ANOVAs? Haha. Well, there's actually a really good reason for that, and I'm not going to tell you right now. And why am I not going to tell you right now? Because after I go back to my office, I'm going to publish the video on ANOVA, which is going to tell you why, okay? I forgot to do it before the class, but that's one of your homework questions. Why don't we just use lots and lots and lots of t-tests, okay? And there's a big problem. So you've got 2 questions here. What does it mean to say there's an interaction? Okay, which we just talked about. And then we use ANOVA for 3 or more tests, or 3 or more data sets. Why don't we use just lots and lots and lots of t-tests? That's your homework. That's for next week. I will see you on Thursday, unless does anyone have any questions before we wrap up?